you're picky for a reason, because those measurements are important. And when we went to measure, we were studying sound waves, and if you didn't measure the right length of string to make your sound with, if you're off by just a little bit here, a little bit there, it didn't do the same thing that his did. So you mess up your experiment. So it made sense after the fact. So y'all just be very precise with your measurements. That's the lesson involved there. So number 2, ask us to take this picture with all these points on there and create segments from point A to the other points on the diagram. And then we're going to fill in this table with those segment lengths. So we're going to draw the segments from A to each of the other points. So from A to B, you're going to draw a segment. And then from A to E, you're going to draw a segment. And then from A to D and A to C. Whoops. And then we're going to measure each of those segments and put it in centimeters and then meters. So we're going to convert a little bit here. The good news is the metric system is much easier converted than the standard system that America uses. There's a reason that there's only one country that uses the standard units, and it's us, and everybody else in the world uses the metric system. So let's measure those segments there. And I'm going to go over here to the paper and measure and see if I can get as close to the same as y'all's. So you should have 1, 2, 3, 4 segments that you're going to measure. From A to all the other letters is the only thing that it asks us to do there. So from A to B, I'm getting 1.7. Is that what y'all are getting? So I'm measuring on the paper here. So line segment AB is 1.7 centimeters. And let's just go ahead and measure them all and get them in centimeters, and then we'll convert them all into meters. And then I'm going to do A to E because it's just right there. Center to center. I got 6.2. Is that what y'all getting for A to E? And you may have went a different route than I did. Let me go back. I messed up. I went back to my screen instead of my paper. I forgot I was going by the paper instead of the screen. Let me do that again. I'm so used to writing on the screen all day, and I forgot I was going to do the paper with you guys. So on the paper, I'm getting 4.5 right on the money. 4.5 centimeters. A to C. Yeah, I would shoot at 4.3 because it's past 4.2. So yeah, A to C, I got 4.3. And then A to D, 2.6 looks like the right number to me. 2.7, 2.6, it's about halfway between there. So we're going to a millimeter. So yeah, either one I would take. So 2.6 or 2.7, whichever one you got there. And then the length in meters. All right. So how many centimeters are in a meter? You guys know that? 1 meter equals 100 centimeters. Okay. So 1 meter is 100 of those little dudes there. So it's a long freaking ways there. So if we're going centimeters, and the prefix CENT, a century is 100 years, right? Centa is 100. So that's the way the metric system names things really makes a lot of sense. When you talk about kilometers or kilometers, kilo is 1,000 is what that prefix means. So 1,000 meters in a kilometer. So the metric system, the way they name things makes a lot of sense. We were smart in our standard system and said, okay, we're going to have things called ounces, and then we're going to have things called cups and pints and quarts and gallons, and none of that makes sense. And then the metric system, they were like, oh, let's just make it easy, and everything's a base 100 type thing. Yeah, it's much easier to do. So for every centimeter, or every meter has 100 centimeters in it. So what that's going to do is move the decimal place. 1.7 centimeters is going to move the decimal place 2 places to the left. So that's going to be 0.017 meters. And this would be 0.045 meters. This would be 0.043 meters. 0.026 meters. Yeah. Yeah. That's the rounding to one. The nearest millimeter would be the in between, because each centimeter is broken into 10 parts, and a millimeter is a tenth of a centimeter. So that's the point whatever. That's the millimeter. No, you don't have to convert it into millimeters there. Yeah, it's the point whatever is the nearest millimeter is what that is. If you were going to convert centimeters into millimeters, you would move the decimal 1 place to the right. So 1.7 centimeters is 17 of the little small marks on your thing. So that's 17 millimeters. If you're going to write it completely in millimeters, it would say write the measurement in centimeters and in millimeters. But it says round to the nearest millimeter. That means, okay, that's a rounding issue there. So we're just gonna write it with a rounding there. And I'll try to be more clear on the test and everything for that. Yeah, but good looking out there. All right, flip over there, and we got another picture similar to that. And they're asking us to use a ruler and a blue color pencil to draw a quadrilateral B, C, D, E. So what's that word quadrilateral mean? Yeah, it's a four-sided shape. That's all it means. Big word for four-sided shape. Doesn't necessarily mean anything about what kind of shape it is. It's not a square. It's not a rectangle. It's just got 4 sides. That's all it means. So I'm just going to use, and if you don't have your blue color pencil, that's okay. Pick a different color. Don't be too picky on the practice here. But when you go to your homework, make sure you kind of try to follow those. So B, C, D, E. So I'm going to draw my lines from B to C. And then C to D. And then D to E. And then B to E. To finish the 4th side there. So we're just connecting the dots there. And we've drawn that picture out of that. And determine the length of each side of that quadrilateral to the nearest tenth of a centimeter. And then express your answer in millimeters. So this one, we're going to convert it to millimeters and kilometers out of this. Okay. So express your answer in millimeters and in kilometers in this table. So we got sides to BC, DE. So BC, side CD, side DE, and side BE. So that's the order I drew them there. So I'm going to try to measure. I'm going to measure again on my paper because when I copied it, I stretched it or something to get that. So from B to C, and we'll just get all our measurements in centimeters, and then we'll go to do the conversion. So from B to C, I'm going to say 6.3. That's what I was about to say, 6.3. And then from C to D is the next one that I've got listed. And it doesn't matter what order you wrote those in there. That's just the order that I drew them in. So that's the order I was going to measure them in. I got 3.3. 3.3 is what I've got. You got 3.4. That's really close. I'm going center of dot to center of dot. And it's, to me, the dot on D is in between the 2 and the 3, closer to the 3. I'm going to go 3.3. And then from D to E, it's the longest one. So this is the one that could screw things up here. Center of dot to center of dot. I got 8.6 or 8.7. It's about halfway between those two. I'm going to do 8.6. And then B to E. Center of dot. Center of dot. 4 point. I got 4 point. No, excuse me. 6.2. 6.2. 6.2. All right. So centimeters to millimeters. 6.3 centimeters is how many millimeters? 63 millimeters, and mm is millimeters. And so that'd be 33 mm and 86 mm and then 62 mm. One, or yeah, you shouldn't be like half of a centimeter, 5 millimeters off. You should be really within one there. I'm not going to say you have to be perfectly the same as mine, but you shouldn't be very far off at all. Like one, we should be within one either way. And then kilometers or kilometers, whichever way you say that. I've tried to adopt the kilometers way of saying it, just because I like how it sounds. Not because it's any more correct than the other one, but most of the world says kilometers. So how many meters are in a kilometer? 1,000. How many centimeters are in a meter? 100. So how many times do I move the decimal from centimeters to make it kilometers? So I moved it how many times to make it into meters? 2 to the left. And then I'm turning meters into kilometers. So 3 more to the left. So I'm moving it a total of 5 to the left to get from centimeters to kilometers. So 5 to the left would put 4 zeros in the front. And km. So in context of a classroom situation, would you ever anticipate like a center activity of measuring, that you would be measuring things in kilometers? No, I mean, if it's a center thing, it's got to be something on the tabletop size. So centimeters or millimeters is probably going to be the measurement that you use, unless maybe you're doing a center where they measure each other's height. And then a meter would probably be the appropriate stick to use, because I'd hate to have to do this and then stack them up. That stinks. But if you had a meter stick or a yardstick, if you're going to use the customary units or standard units that we use in the States here, that would be that. There's a step thing, and I'll try to find the PDF of it and include it, that takes you through all of the different ways of doing the metric system, where it puts the original unit in the center, like meters or grams or liters goes in the center, and then steps it up and down for that. Y'all remember? Did y'all ever do that in school? I remember it from science class. Maybe I showed it to you. I don't know. But it's a step type thing where you put your original in there, and then it shows you where the kilometer and all the prefixes that go with those things. The ones that are used most of the time, centa, milli, and kilo are the ones that are used the most in the world. but there are a bunch of there are several in between those that could be used. And I'll try to find the PDF and attach that to the announcement for this week, so that you just got that, and it'd be a handy resource to hang on to out of that. Because I remember science classrooms when I was a kid having that on the wall. I could see Miss Gloria Jean Stanford's wall over at Adams Elementary School having that on the wall. I remember the steps, and like she had a little person that would walk up the steps that she taught us how to do that with. She was a mean lady, but she was a good teacher. She expected good out of you a lot. She was a really good person. On blank paper, use all 7 tangram pieces to make a large rectangle, and then measure the size of that. So we're going to take our tangram pieces, and we're going to build a rectangle. So find us a piece of paper. Find you a piece of paper. Just a piece of notebook paper is fine. And you're going, excuse me, and you're going to make a large rectangle. Yours may not match your buddies, okay? It's okay. So we're just going to take those and try to make that rectangle out of that. So got to do a little practice with the tangrams today. Everybody loves tangrams. Yeah. Yeah. Uh-huh. I'm going to tell you now that there's something about that. You struggled with it. Oh, that's okay. That's all right. Nobody says you got to be perfect at them. I'm out of practice with them. I don't do them nearly as much as I should. So to enjoy them, I really don't, because I do enjoy them. Oh, me. Excuse me. Do what? You got to arrange them in the right way to make, there's one. I'd say take a picture and text it to us, but so she's got one.
All your pieces?
Feel free to get up and walk around.
Okay.
Yeah, you got to use all of them.
Darn.
So there's one. That's not the only one.
Why did I have 6 pieces? Wait, that's not all of them.
Yeah, there's supposed to be 7 pieces.
See, I did that too.
You're missing a piece. Uh-oh.
I was like, look at me. I can't, of course, just stick on the end like normal.
Do what?
I said, of course, just can't stick on the end.
No, of course not.
Well, that makes me wonder about my homework and my use, because I make all them shapes. I wonder if I lost.
It may have been why it was so easy for you. You didn't use the one.
I
think using your
it was in
tangram.
my folder, so yeah, I did use it.
Oh, okay. Oh goodness, that was a bit bad news.
I was like, I worked
Bad news.
Yeah, me triangle.
It's not possible.
It's not. This is not how my brain works. It's so bad.
Oh, bless you.
Numbers, I can do like that.
But you know what? There's a lot of people can't do numbers. You know it?
Why does you do
I teach them every day. Just give me.
my nephew can do Rubik's cubes like at a really crazy. That's great.
Yeah, I had a student one time. He had a Rubik's cube, and he was sitting around in the library just flicking it around and solving it. And I said, how'd you learn to solve that? I just looked up all the algorithms. I said, what's the algorithm? He said, it's the order you do that stuff in. I said, do you know what an algorithm really is? It's a mathematical process. I said, you know what you don't do for me? Your homework. And he said, oh, well, you're right. I don't. And he didn't. But he could solve a Rubik's Cube, but he couldn't do it. He didn't understand. He didn't understand that solving that Rubik's Cube really didn't get you anywhere. Didn't help you. Algorithms, he said. And I said, oh, it's algorithms. Good for you, man. Sure. I feel like I could cut this one and it would work. Can I cut that one? Frustrated.
Okay, I got it.
I get
All right, I got it.
Katie's beat us all again. And she used all 7 this time?
Yeah.
This is my, I'm not sure you did. Yeah, sure, you said that last time. she said, I'm not worried about getting steps in. Nobody's logging my miles here.
She does have it.
Does she?
Oh, wait, I did it.
Hey! Stumbled into it. Y'all have the same one? I'm gonna take pictures this day, buddy.
So in case I move it by accident?
That's a nice one. I like that. Good job. Is that the same one?
Oh,
The same
okay.
one? That's awesome.
Oh, check it out. So then we need to draw that on.
Yeah, and then draw that and then measure it. I don't know if you got room on.
Drawing a rectangle?
Yeah, but it's got to be that one. That one.
Wait, no, I don't got it. On a piece.
I'm gonna swap to this thing
Take it apart.
and show you.
So you have to write.
Zoom out. How do you do that? Boom. All right, focus. You can use.
No, I don't know what you did. I still don't get it. Okay, you take these ones and then you're next to these.
Yeah, the medium goes in the middle. Like that.
Oh, that isn't close on mine.
No. I'll kind of explode mine a little bit so you can see in between the shapes. You see the gap between them there? And put enough gap there.
Just the rectangle.
Yeah, just push it close together and then trace that rectangle that it creates. And you're going to measure the sides of that. Yeah. We talked about this last week and the fact that you don't get better at these. And it's like you said, you got those kids that are running around and they're their brains.
So mad. They're like 8. I just want to
Yeah, it frustrates me when my 8-year-old outdoes me on some things.
And she's like, hey, you gotta measure all the time.
Then just trace around the outside and measure trace around the outside. And if you'll lay your ruler on top of it, like that, and then press on it like kind of widely, that'll hold them all kind of in the same place. And then we're gonna and then you measure those sides, and so doing the same things that we've been doing there. So I'm gonna. So I'm just going to draw a sketch of a rectangle here, and y'all going to tell me your measurements. And I'm gonna put the shapes in there because I'm recording this for Casey. Bless her heart, she's got the stomach bug. She decided not to come share with us. Yeah, I told her thanks.
Yeah, she did. She thought
Keep your old germs. Hey, y'all, we're recording this, so y'all don't say nothing bad about it. Okay, see if they say something bad. I didn't do it. I tried to stop them. No cyberbullying. It's going on YouTube. And then we had the medium one, and then we had the trapezoid. Yeah, make the rectangle and then measure it. Measure the sides.
Yeah, I need to make that moving so I can.
I mean, you're right there. I'm trying to.
What'd you say?
Go back here. To,
I'm gonna make my rectangle look right.
you should have 90 degree corners. All right, so that's the ways you can make a rectangle with that. Absolutely, it's a rectangle. So whatever you measure one side to be, the other side will be the same. So somebody give me a measurement so we can move on. 7, how many?
Wait, what? I used the, on the top and the bottom? Got that on the side?
You got 7.2 on the sides.
I don't think I wrote it on the side. Yeah. And then the top, I got, oh, yeah, that's 7.
How much?
14.7. My top was 17. Well, mine was 5. Oh, okay.
If you're using the little foam ones, it would make sense that whatever the length of the side is, the top should be almost twice that, because they're the same side, because the side pieces are the same out of that. So 7.2 times 2 really should be 14.4, but I'm sure there's a little bit of a gap there because the foam kind of is rounded. That's just using the foam one.
The top and the bottom line be the same?
Yes, they should be the same. Y'all using the printed one? Yeah, they should definitely be bigger. Yeah.
Okay, there's red one.
Yeah, so when you're, and that's the idea, is that you trace around them and then take all your shapes off of it and measure what you trace, or measure the rectangle you created is out of that. So this is, the red is with the foam stuff. If you use the paper one, you guys give me a measurement for the paper ones. What was your side lengths? The short side. 9.2. And then on the long side, I'm using the little foam ones that are coming to thing. Are you using some out of that box over there? They're a little different because they're hard plastic. So they're going to be a little bit different. That's right. You're on the right track. 17.9. That makes sense. About double that. About right. Okay. All right. Label lengths you're on nearest 1/10 of a centimeter. So 0.1 decimal place. All right. Activity number 12. Moving on. In the grid below, draw 2 different polygons, each with a perimeter of 16 centimeters. Each of those boxes on your paper is a 1 centimeter by 1 centimeter box, or is intended to be that way when they were created. Oh, and they are precisely 1 centimeter by 1 centimeter if you measure them. Success. I did pretty good on something finally. All right. So what's a polygon? Yeah, it's a closed-in shape. No arcs, no curves. Got to be straight sides and corners. So polygon is just, and we're just drawing 2 different ones that have the same perimeter of 16 centimeters. Okay. So let's take a stab at this. I'm going to draw the easiest one, and that would be that one, a 4 by 4 square. Right? It has a perimeter of 16 centimeters. No, you just got to make sure you got room to get 2 in there. Doesn't matter where you draw them. So each box is a centimeter long. So the perimeter of the whole figure, so this is 4, this is 4, this is 4, and this is 4. So the whole thing, that adds up to be 16. That's the easiest one. I could also draw one that is 2 centimeters tall and 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 6, 7, 8 long.
Sounds like a quick
Hold
question,
on.
Ellie.
Not 2 by 8, but 2 by 2, 4, and then we need 12, so it needs to be 6 long.
So if I was like, the state could ask me this question, maybe I said that, 16, like I know 4, 4, 4 on each side,
Mhm.
that's all. But whenever I started writing down, I thought like how a kid would say it, and you would count the squares all the way in, like 1, 2, 3, 4, so you get 16.
Uh-huh.
You see what I'm saying?
I see what you're saying. Okay, so you could have an odd shaped polygon that would work. So you could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
Okay, so that's how I could show.
Yeah, you could show.
About how it's the side of each.
Yeah, exactly. Yeah. I'm glad you asked that. Perfect. Yes. Yeah. That it doesn't have to be a nice rectangle or square. Polygons don't always fit that shape. They're just closed figures, right? So an odd shaped one could work too. One kind of the shape of one of our pentominoes, something weird shaped like that might be something that could be useful to do that perimeter out of that. So 16 has got to be the perimeter. It's just got to be the measure of how around the outside. It doesn't necessarily have to be a square or a rectangle. It can be something else out of that. So, yeah, so that actually is more informative to a student than one that's 4 by 4 by 4. That to me,
Right.
a student really understands perimeter then better that it's each side adds up instead
Not like
of
that whole chunk of square.
Yeah. Yeah.
Like how my
Right, exactly. Okay. Now, I've done 3 here, so we're gonna I'm gonna do all of these. For B part, it says find the area of each of your polygons in part A. So I'm gonna number this one number 1, number 2, and this is number 3. And area is what? What's the difference in area in? You don't have to have that third one. I'm just using it as another example here. Uh, so, what is area versus perimeter? What's the difference? Yeah, it's the inside part that's the area. The perimeter is the rim. It's the outside of that. So the area is the space in between. So finding the area, we're going to count up the blocks. So total number of blocks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 blocks. So the area of shape 1 is 16 square centimeters, or centimeters squared is the notation. No, that you're trying to eventually you would be trying to build up to those formulas about if it's a square, it's going to be length times width. Length is 4, width is 4. Notice there's 16 boxes inside of that square. So the idea is bridging that between counting boxes and developing formulas out of that. So you're that in between step that hopefully you're getting a chance to teach, because that's the fun stuff, is when you get to do the light bulb moments that are like, oh, I remember that now, and that makes sense now. Those are fun. And my polygon number 2 was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2 and 2 is 4, 6 and 6 is 12, so that's 16. So polygon number 2 had an area of 12 square centimeters. And then my extra example there, that number 3, has the 16 as the perimeter, but the area is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the idea is the relationship here is not that everything with a perimeter of 16 doesn't have the same area. You guys have different shapes on your thing. Yeah, so they're going to be different. Okay, so a polygon, just having a perimeter of 16 doesn't lock it into always having an area a certain size. Okay, so keep that. That's kind of the idea there. Next page. On the grid below, draw a picture of your W pentomino. Remember the W pentomino and find the perimeter of your W and show how you counted to find the perimeter. So the W pentomino, remember pentomino means it's got 5 blocks in it. So don't forget that. So I'm just going to draw here. Yeah, you can put it any which way you want. So there's my W pentomino, and I'm just colored in so you can see it better. It's kind of like anything else. The more you've done it, the less you have to think about it or look at it. So I like pentominoes. Did y'all play that game that I sent you the link to? You need to go play that game. It's addictive. The little pentomino. In the announcement that I sent last week, there was a link at the bottom of it that was an online pentomino game type thing, and it would. Well, it's similar to that, but this one is like it would give you a shape, and you had to take the pentominoes and drop them in there and flip them and turn them. It's kind of like what you were doing with homework, but it would give you random shapes, and you had to fill it in with the pentominoes. It was a pretty fun game, and it'll help you with your spatial sense. You guys saying that you're struggling with the tangrams and things. Actually, playing with the pentominoes will help with tangrams because it's. Yeah. Yeah. I've seen some ads for some apps, the game apps like that. Yeah, and those are fun games. And if you're lucky enough to have an iPad in your classroom or something like that, you find those apps and download them and let your kids play them in one of the centers as a spatial sense type thing, because that's one of your standards that you're trying to do. All right, so we got the W pentomino drawn in whatever orientation you want to do that in. It's the same size no matter what. And we want to find the perimeter of that. So perimeter is distance around. So 2, 3, 4, 5, 6. So to show how you're counting, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perimeter of 12. Be careful, don't skip that side when you turn the corner. That's the easy one to forget. So 12 perimeter is 12 centimeters. That's again, that's centimeter by centimeter blocks. Use those again there. And showing your counting there is plenty of explanation.
And it's only squared though with area, right?
Yeah, area is the squared thing. Volume is cubed. And linear distance, like perimeter, is just the plane. And we'll get into 3D shapes before we get out of this class too. I've got a nice set of them that we'll play with a little bit. Is it? You like geometry stuff? Yeah, it's fun. All right.
The little upside down Christmas trees where you figure out who you saw for X. That's my favorite thing. I can do that too.
I don't know the idea what you're talking about. All right, so find the circumference of the circle below and label any measurements you need to measure. Show your calculations. Okay, so got to go back to general knowledge here. How do you find circumference of a circle? It's a formula. How do you find 2 pi r is one way. It's also pi times diameter. Both get the same result. The difference is one uses a diameter, one uses a radius. What's the difference in diameter and radius when it comes to a circle? Yeah, radius is half of the diameter. So you've got to have the center point to get the radius. We don't have a center point here, but we're going to have to find it probably. So how do you find a center point of a circle when it's not marked? You could fold it. Unless it's a record, a vinyl. If you're going to fold a vinyl, you're not going to have a vinyl anymore. I had a professor in college. I took a trig class at Jackson State, and the guy he was super nice to me, but he was so picky. He didn't like he had a compass and he would draw circles with the compass, but it wouldn't leave a center point in it. So he comes to class with the big vinyl record the next day, and because it has a hole in the center of it, and he can hold that vinyl record up there and put the marker in the hole, and put the center, and then trace around the outside of it to get a circle. And he had the center point still in there. He liked doing that, and then he tried using like a string and a marker. Y'all ever made a compass that way? You take a string and tie it to your marker and hold the string here, and your marker will only go the length of the string away, and that's how you can get that. But he used a record for the rest of the semester because he loved how precise it was. It's beautiful. I didn't really think it was that impressive. To be honest, I was like, it's just a circle. My circles, and, you look at my circles on my paper, and even though that's a pretty doggone good circle, mine in college were a little less than to be desired. They didn't quite make circles out of it. So the way that you would find the center, the best way is take your ruler and then just drag it across the circle, and look for, set the edge on the 0 mark of your ruler, and then try to find the widest spot. So like with your ruler, go on the edge of the circle and stretch it across. Like this was not long enough for the screen, but put the 0 mark on the edge and then pull it down. It's going to be somewhere close to here, and then you're looking for where it gets the widest. And when you pull it across, what I'm saying, so you got, it's going to be somewhere around like right here, right? So you can put the edge of your ruler on the edge of the circle, and then look over here and see when it starts going down, then you've gone too far. Back up, and then when you find the widest spot, that's the diameter.
So
Folding it is a good way if it's a single piece of paper, but.
can you say that again?
Ow. All right, so let me do here. Show you what I'm talking about. What I do with my ruler, I laid it on the desk. All right, so the idea that I kind of like to employ is to take your ruler, and you got your circle laying there. You take your ruler and find the edge here. It's going to be somewhere in this area of the circle, right? Notice on the left-hand side right here, I'm putting the 0 mark of my ruler there. And then I'm pulling the ruler across the circle, but keeping the 0 mark on the edge until it gets to the widest spot. When it starts getting narrower, then I'm going to back up and find that widest spot. That widest spot looks to be about right there. And I would draw what I think is the diameter. If I want to be real precise, turn the paper and do it again. Because if I turn the paper and do it again, where I think the widest spot is, those two lines are crossing at pretty close to the center of that circle. I just rotated the paper 90 degrees or something like that. If you were really wanting to do it with you could do it with a compass, where you use the arc length measure of a compass. A compass is, remember those sharp pointed things that had one end that comes out, and you make a circle or arc mark with it. You could do that with this and find the center that way. But that's not that thing. Yeah, one of those, you could measure it with that. That's and you could adjust and get it to the center. Yeah.
You gotta know how to let it out.
You got to spin the screw at in the center. Yeah. One way's in, one way's out. You got a really precise one there with that. So you could,
How do you know where to put the points?
If you still got to go edge to edge on the circle, and then when you do that, edge to edge, it's hard to do without one because I don't have one with me. You can put an arc mark up here, and then do the same thing down here. I'm running out of paper. I'm going to recall my good old art class stuff here to get that happening. And then when I connect those two lines,
I can't get it in time.
and that actually is the center of that. So if I had a better compass, I was a little off there because use my hand as a compass instead of a real compass. So get close to the center. That's what I'm trying to tell you. Get it as close to it as you can. You're not going to be off by very much. Okay, get as close to the center as you can, and then we're going to use that formula for finding the circumference of our circle. So we got to measure the length of said diameter. Okay, so measure how far it is across your circle. 9.2 looks about like what I got. 9.2 centimeters. So that's the diameter. So to find the circumference, it's 9.2 times pi centimeters. Or a decimal approximation for that would be 9.2 times 3.14. What's 9.2 times 3.14? Go ahead and do the decimal because that's the most common thing done in elementary school math is to do the decimal 3.14, and we're getting 28.88 or 89. Did you use the pi button or 3 point? All right, so don't use the pi button. Use 3.14. Yeah. So I'm going to use go round to 2 decimal places there because our measurement was rounded to 1 decimal place. So anytime we do a calculation, the most we can go is 1 more than what we measured. That's the rule in geometry anyway, is that you can go 1 more than what you can measure. And our rulers are calibrated to 1 decimal place. So we can go 1 more than that when we round. So there's circumference of circle. Activity 13. Area, perimeter, and circumference again. Do a little bit more with it this time. So area, circumference, and perimeter, all measurements of shapes. And when we're dealing with area of shapes, what is this shape here called? A parallelogram, that's right. And the area of a parallelogram, the formula for that is base times height. Okay, base times height. I before E except for C. Is it H? No, I spelled it right the first time. Yeah. Base times height. And the base is going to be the side that the height runs into. And that height, the copy didn't do well here, but there's a dotted line that goes here, and that's supposed to be a box right there for the 90-degree angle. An altitude or a height of an object is a perpendicular line measured in there. Notice it's not the length of the side, that slanted side in the parallelogram. If it's a rectangle, the height is the actual side because it meets at a 90-degree angle. So parallelograms are a little bit different because they don't meet at 90-degree angles always. So we need base times height is our formula. So in our case, it's 15 times 18, whatever that is. Say again. 270 watts. Centimeters squared. What shape is figure 2? Say it again. Trapezoid. Yes, we love trapezoids at our house. They are fun shapes. What makes trapezoid? Two parallel sides and a pair of non-parallel. So that trapezoid is kind of turned this way. If I lay it down this way, it looks a little bit more like the trapezoids we like to see. It looks a little bit more familiar if you lay it sideways out of that. But the formula for area of a trapezoid, does anybody know that off the top of their head without hitting up Google or Siri? 1/2 base 1 plus base 2 times the height. The bases are your parallel sides. So your parallel sides are your bases, and then the height is again going to be measured at a 90-degree angle. We can tell in this picture that 90-degree angle happens on that side. Do what now? We don't. Yeah, it doesn't even matter what that angled one is out of there because we don't need that. We only need the height, how far apart are the parallel sides, and then the lengths of the parallel sides to find the area of a trapezoid. The way I remember this is, does anybody know how to find the area of a triangle? Yeah, everybody remembers that one. If I take that and cut it right there, what's this shape? That colored in shape's a trapezoid, right? So it helps me remember the formula for area of a trapezoid is a lot like the area of a triangle. The base is just different because we got two different bases on a trapezoid, but only one base on a. What happens is if you, has anybody ever heard of Geogebra? There's a free thing. I'll send you a link to it. It's awesome. It's a free program that's online. It's an internet-based program now. It used to be a download program, but now they've made it web-based, HTML5. It's awesome. But it's free geometry sketchpad, basically, is what it is. And you can create these shapes. And what you can do is you can create a trapezoid where you can make a slider on it to where it will change the lengths of the bases for students to play with. And what happens when you take the base of the top here, as you make this base smaller, it gets closer and closer to being a triangle, right? So as that top base, as you squeeze it in, it becomes a triangle. When that top base is 0, it's a triangle. But as you stretch that top, the points here apart and create another side, that makes a trapezoid out of that. And then you can look at the areas of that and see the relationship between these two formulas out of that. It's a really neat thing. I'll try to remember to send you the link to that and let you play with that. That may be one of our projects on one of the journals, is to look at a GeoGebra thing that maybe I built or I find somebody else has already built it. There's a ton of stuff that's already built that you can just use. It's open source, so it's free software, no copyright or anything to it. So it's awesome. Such a good program. All right, so for this one, we're going to plug in the stuff we know for this trapezoid. Let's go ahead and move along here. Base 1, it doesn't matter which one you call base 1, which one you call base 2. I'm going to do the 22 is base 1, the 16 is base 2, and the height is 11. And I'm working that out. 1/2 times 38 times 11 ends up being 11 times 7 or times 418, and centimeters squared again. That's what the dimensions are in. So that's the area of that trapezoid. You didn't do that by half?
No,
Oh, I thought you had already done that by half. Okay, 38 times 11 is 418, or 4 whatever, and then times half would be 209 square centimeters. Sorry, I thought you had already multiplied by half. I don't know my 38 times tables.
I had to add the extra stuff, like I had to.
That's fine.
put it all out.
Absolutely fine. Out of that, no problem there at all. Okay, but end up with the 209 square centimeters on that. Okay, so number 3, they didn't draw us a picture, but it said a circle with a diameter length of 7.8 meters. There's a reason they didn't draw a picture. 7.8 meters is how far? It's pretty good ways, right? A meter is a little over 3 feet, right? It's 3.2 feet or something like that. So 7.8 meters is almost 8 meters, which would be almost 9 yards, which is 27 feet, which is about the length of this room. Probably 27 feet is probably. Well, this way, not that way. That way's a little further. But anyways, 7.8 meters. We got a circle. It has a diameter of 7.8. Now, what's the formula for area of a circle? Nope, that's circumference. These are supposed to be general knowledge things. Yeah, that's area. Pi r squared. And the joke that my dad always says is, no, pi r round. And no, that's what my dad always said. Pi r squared. So we got to have the radius. What do we have for this circle that we've drawn here? The diameter. What is the radius? So we're going to take half of the diameter to get the radius. So we're going to take 7.8 divided by 2 and get 3.5 plus 0.4 be 3.9 meters is the radius. Okay, and then we can take that and plug it into 3.14 times 3.9 squared. And that's going to give us our, I guess I could open my calculator here. 3.14 times 3.9 times 3.9. 47.76. Go 2 decimal places there again, because our measurement was in 1 decimal place. We go 1 more than what we measured. And it'd be meters squared here, because our dimension was in meters. Out of that. So, knowing those formulas, that's an important thing. They have gone away. Used to, probably, Maggie, you probably took end of course tests in high school, and they gave you a formula sheet, didn't they? Yeah, they weren't T and ready tests when you took them, were they? Or anybody else? Okay, so they were EOC tests, and you had a formula. Yeah, they were, and T and ready has gone away from formula sheets. Like when you take the geometry EOC test now, or the T and ready test, there's a formula sheet, but it ain't got nothing on there that's useful. I mean, it's not. They don't give you the formula for area of a circle or circumference or any of that stuff. On ACT, you don't get a formula sheet ever. For EOC, you don't get much of a formula sheet anymore now either. Used to the formula sheet for EOC had quite a few things on. There wasn't a geometry EOC. There was a algebra 1 and algebra 2. And then geometry you didn't have. They didn't do an EOC for no apparent reason. But the formula sheets are going away from letting kids have those for the reason of the ACT doesn't give you a formula sheet, so you need to commit those to memory is the idea there to that. So as you're going along there, us high school teachers would appreciate younger grade teachers making them memorize formulas. That would be nice. Because they don't know them when they get to us. 4, circumference of the same circle from problem 3. What was the formula for circumference again? Pi times diameter or pi times 2 times radius, right? So whichever one, I'm going to use the pi times diameter because that's the measurement they gave me. So 3.14 times 7.8. 0.14 times 7.8. And again, use 3.14, not the pi button on your calculator for what we're doing. And totally didn't get that number. 24.49. And it's in meters, not meters squared, because we're talking about a distance around. Be careful on your units. That's one thing that I'll be looking for as we're doing this. You mean the approximate sign? I'm not going to be picky either way there. Technically, it's approximately, but I'm not going to be picky about that. Just make sure you got it rounded the right spot and the correct dimension on it. We're good. All right, 5 says, find the area and the perimeter of this triangle below. Use your ruler to label the appropriate measure to the nearest tenth of a centimeter. So what about this triangle is important to note when we go to find the area of it? What kind of triangle is this? It's obtuse, which means what? What does that mean? What's greater than 90 degrees? One of the angles is greater than 90 degrees. So because this is an obtuse triangle, then we have to measure the height or the altitude of that triangle in order to find the area of that. So we're to find the perimeter. What do we have to do? Got to measure all sides, right? So let's do that first. I'm gonna do it on the paper just like you guys. So center of the outer edge to the center of that. So the top side there, I'm getting 7.3. And I'm just doing from center of that corner to the center of the outside corner. And I've got 5.8 on this right hand side. If you're you're way off. 5.9 is acceptable. 6.0, you're not being precise enough. Don't go inside edge to inside edge or out. Go center of the corner. Like so, when you lay your ruler up there, get the edge, that 0 mark there right in the center of that corner. Out of that, and then when you go down here, your other mark should be toward the center of that thing there. That'll help with precision. And being very precise it sounds picky because it is. Because you want to be picky because your students will be less picky than you are. So the more picky you are, the better answers you're going to get. And then for the really long side, y'all getting 10.7 is what I was thinking. Is what I was getting, 10.7. Now, so perimeter is just going to add all those up. So 7.3 plus 5.8 plus 10.7. That's perimeter. And so 7.3 plus 5.8 plus 10.6, right? 10.7, sorry. 23.8. One up from that. Yeah, and the key, I'm gonna look for the original measurements, and then your calculation from that should reflect that. So this would be centimeters. Now here's where the area comes in, and this is where we got to find that altitude. So to find the altitude, what you've got to do is go from one of the corners and then down to a base. Okay, so if I tried to measure an altitude from this corner down to a base, I've got to drop a 90-degree angle into one of the sides. Well, if I drop 90 degrees from this, it's not going to hit this side. And if I drop 90 degrees from this corner, it's not going to hit the other side. But if I drop 90 degrees from here, it will hit the other side. So that's the best one to go by. Go from your obtuse angle, if it's an obtuse triangle. That's the easiest thing to do. If it's an acute triangle, it really doesn't matter which one you go from. You can drop it with the protractor, or you know, I'm gonna measure it with a 90-degree mark there. So again, get your protractor in the center, the circle in the center, and we're gonna measure it to drop it at 90 degrees from the base. So we're dropping to the, you're going to go 90 degrees from the base to that corner. Actually, you're going to line up. Let me show you. I generally don't like these elbow things, but it's kind of handy in this class. All right, so I want to go from the zoom out a little bit there. All right, so I want to get a 90-degree line that goes from this corner down to that side. That's what I want. Okay, so I need 90 degrees to be down here. That's where my 90-degree angle needs to be. Okay, so that's a little trickier, but the idea here is you're going to line up. See how I'm lining up this line right here with that base? See how that's laying right on top of that base? And then I'm going to kind of try to scoot it. And it might help to have a straight edge or something. It goes to the 90 degrees until it gets to that corner. Not too far. I'm trying to line it back up here. Be as picky as you can be, okay? And then, so you would then, okay, that's where it's happening at. That's the point. And I'm going to draw my line down. And it doesn't matter if it goes on through, because we're going to measure that length of that segment right there. It's got a little bit of an angle on the picture, so it doesn't look quite perfect. Right. So we get a 90-degree angle down here. That's what we're trying to get. So when you draw, I'm going to draw it on my screen here. That pen won't right on. It should look something, you know, like that with a 90-degree angle. You're going to get real close either way, and then I'm going to measure that, the length of that line. I'm getting somewhere in the vicinity of 3.7 is what I got, somewhere around 3.7. So you're measuring from where it hits the base, which is the long side, to that corner, the length of that line. 3.6, maybe 3.8. Yeah, 3.7, 3.8, something like that. So to find the area, then it's 1/2 base times height. The base is the side the height comes out of. So that 10.7 times the height, which is, I got 3.8. Multiply all those together. 1/2 times 10.7 times 3.8. 22.33. .5 times. Did you ever get 3.8 for the height? And your base is 10.7 times 3.7 times 0.5. Close. Yeah, it's going to get the calculated values are going to get off if your measured values are off by a little bit. Your calculated gets off more. That's one of the reasons that you want to be really picky about your measurements, because as you do more calculations with them, here we're doing 3 multiplications and we got off by almost half of a whole centimeter or square centimeter in this case. So being precise with your measurements, that's one of the reasons, is because then if you're off by 0.2 on every measurement that you make, and then when you do the area of it, you're going to be off by quite a bit out of that. So that's one of the reasons to be real picky with your measurements there. And that's okay. I'm going to see, you're going to show me your measurements here. So I'm going to see those, and I know that if they're off by a little bit here, it's going to be off by more there. And I'm smart enough to figure, not be that crazy about it. Just as long as you're going to be close there, and that's okay. One of the reasons I try not to do multiple choice on this stuff, because you measure it and it doesn't measure the same thing as what I did, the multiple choice option you get, it's not there. So it makes it tough. All right, so 6 is a really easy one here. We're going to convert, and we're going to show our calculation as to how we're doing that. So that's going to be our explanation, is showing that calculation. So 2.8 kilometers into centimeters. So what I like to do when I'm converting is to show that, hey, I'm going to go through the standard measurement to get down to that smaller one. So how many meters are in a kilometer? 1,000 meters in a kilometer. So if I multiply that times 1,000 meters, then it's going to cancel out the kilometers. That's the idea. And then how many centimeters are in 1 meter? 100. That's the conversion style that I like to see. And all your science teachers said amen to that, because that's the way they like it too. Okay? Because the units cancel out along the way, and you end up with centimeters at the end, because that's the only one that's left. Maybe y'all remember doing that in a good old chemistry class. Yeah, you should. It should be. Yeah, you did have done the same thing. And the idea of the step thing is when you're converting across the same kind of measurements. But this style of conversion is like if you're converting. Y'all remember in chemistry class where you converted from grams to moles, and 6.022 times 10 to the 23rd. That's a mole. Y'all remember doing that kind of stuff. All right. So here's the tricky one here, B part. Square units. Ha. So when we're going from centimeters to meters, it's pretty easy. It's moving the decimal place. But when we're going from square units, it's not moving the decimal place the same way. Okay. So if we're taking 127,350 square centimeters. They're square centimeters. They're not regular centimeters. They are square. And I'm going to convert into meters. Squared. What's a square meter? It's a meter by a meter. It's a meter this way and a meter that way. So it's 100 centimeters this way and then 100 centimeters this way. How many square centimeters is that? 100 times 100, right, which is 10,000. That's where that's coming from. 10,000. And then you multiply there and we get the steps, or divide actually. So 127,350 divided by 10,000. 12 point. And we're going to go all of the decimal places here because we're converting that. 735 square meters. And if you wanted to convert that into square kilometers, you could go the next step along the way. So that's why I kind of show the parentheses and the unit cancellation idea of converting units instead of the step thing, because the step thing works when it's a regular unit, but when you go to square units, it's a whole different game. It's not decimal movement the same number of times. It's multiple times there. All right, 7. Where we at? Use calculated area in figure of problem 1 and convert it to square meters. Show all necessary calculations. So go back to problem number 1 and figure 1 in that, and we're converting that square centimeters into square meters. So 270 square centimeters. Again, 1 square meter is 10,000 square centimeters. So that's going to move the decimal place 4 times. 1, 2, 3, 4. 0.0270, or 270 meters squared. I'll check myself. 270 divided by 10,000. Yeah, that's the same number. Is the trapezoid in that? Was it part of number 1 or was it number 2? It was number 2. What? That's it. Easy enough. 8. Problem 5. Convert our perimeter into meters. Well, that's a straight step, right? How many places do I move the decimal? It was 20. I got, was it 27.8? 23.8. And to convert it into meters, 2 places to the left, 0.238 meters. The calculation that it's saying there, showing me moving the decimal place works. Or you can do 1 meter is 100 centimeters. Do it that way. That's the conversion that we've been doing. That's the same way. Still equal to the same thing. Kind of a boring thing there. And then a lovely spatial sense type problem here with number 9, in which you are asked to take this picture and in 3 different ways show and demonstrate the calculations that are required in finding the area of that said figure. So it's a complex figure is what we call this in geometry. Everybody remembers these on TCAPs and stuff, or I remember them on TCAPs. So 3 different ways to find the area of this funky looking C. So somebody give me way number 1. Nope, that's perimeter.
So, like you can use that big portion to the left, you can make it big rectangle.
So like you're saying like this?
Yeah.
That works. And then so we need to find if we do that, then we've got 1, 2, and 3 different rectangles to find the areas of. So the area of rectangle 1 Well, to find the area of rectangle 1, I need a length and a width. I've got a length. I don't think I have a width, so we need to find that. Yeah, so that means this side here is going to be 32 centimeters. And then go from there. So area would be 64 times 32. (1,984 square centimeters). And then get angle. Let's get the area of rectangle 2. Which is 272 square centimeters. And then last, let's get the area of rectangle 3. Yeah, 32 times 10. I can do that one. 320. And then the total area is add all those up. (2,976). Good job. So we know we should get 2,976 square centimeters every time we do that. On the next two, pick a different way. May not be easy for you to be creative, but you just got to be creative. This is my next way. Yeah, just cut it up in different ways. My way number 3. And then cut this out. Yeah, that's my way number 3. But you pick your ways and you find the area. You're still cutting it up the same way or cutting out the pieces that you're not using. Same idea. It doesn't take any, it's just you pick your ways and go from it. There's not an infinite number of ways on this. There are only a select number of ways that you can do it, but it's easy math for you to do. So cutting that into rectangles there is the best bet. If you want to cut it into triangles, more power to you. I don't think that's the best way. So, but it can be done that way. I wouldn't recommend it. Okay. So we're going to go ahead and go to activity 14, and because you guys can do that kind of stuff. That's easy stuff. All right, another area perimeter, and we're going to get into Pythagorean Theorem in this section. So what do we when we're drawing the figure and determine the area and the perimeter? Round all non-exact area and perimeter values to the nearest tenth. So 1 decimal places are rounded on our area and perimeter. Your drawing does not need to be to scale, but should represent the described figure. Label all given measurements in your figure and show how to calculate any necessary measurements that are not provided. Also, using formulas only that we've developed in class, so don't make up new things out of this. So the normal formulas that we've used for area and perimeter. Don't come up with some. Yeah, don't use the diagonal times diagonal formula if you know that one for parallelograms and rectangles. All right, so again, it says we don't have to draw it to scale. So when it says the diagonal length is 25 centimeters, we don't have to stretch out 25 centimeters and draw that picture. We know it's a rectangle, right? So we're just going to label the spots that need to be the right length. Okay. So for number 1 there, it says draw a rectangle with a diagonal length of 25 and one leg length of 7. Okay. So diagonal of 25, that's that, and a leg length of 7. So I'm going to put the 7 right here. This is my 25. And then guess what? It's a rectangle. So what do we know about the other side? It's it's 7 as well, right? Or it better be. If it ain't a rectangle. Uh-oh. Problem. I'm supposed to find the perimeter in the area of that dude. Ooh, I don't have the base. I don't have the length of the rectangle out of that. But it's a rectangle, and I do have a diagonal. So what does that mean? I can use. Yeah, that old good old Pythagorean theorem: a squared plus b squared equals c squared. We were going ACT prep today. We were doing problems with Pythagorean theorem. They loved it. No, they didn't love it. Is it? You're such a nerd. That's a nerdy thing. I love Pythagorean theorem. You should get a T-shirt. My favorite formula: a squared plus b squared. Oh well, man. Don't tell people that. Don't tell your principal that when you get a job. All right. So, what parts are A, B, and C for that? That's correct. The hypotenuse, which is C, is the diagonal one there. So 25 goes in place of C. Yeah, you get to solve equation type stuff. Yeah. And then I'm going to say B is 7. So, no. And I don't know what 25 squared is. I used to know. 625. And then A squared, subtract to get there. So 625 minus 49, 576. And then calculate that measurement there. So square root of both sides there. So A is equal to the square root of 576. To get with the graphing calculator, to get the square root button, you got to hit the blue second button, and then it's written in blue there. So you see, you got to hit second, and then this button to get the square root symbol, and then type in your number that you want to do the square root of 576. Enter. 24. Works out. It's amazing. It was a good number. So the length of these sides are 24. And then we can then do that perimeter formula, or add up all the sides. 7 plus 7 plus 24 plus 24. 14 plus 48, 58, and 4 is 62 centimeters. And then they want us to do the area. There's perimeter. Area. Which ones do we use for area? The 7 and the 25 or the 7 and the 24? 24. Length and width of the rectangle. So 7 times 24. 168. Square centimeters on your units. Got it. Easy stuff. But good old Pythagorean theorem. Something we've used for years. We love Pythagorean theorem around here. All right, isosceles triangle. What the is a isosceles triangle? What's that mean? At least two sides are congruent to one another, whose congruent sides have lengths of 100 millimeters. So I'm just going to draw an isosceles triangle. It doesn't have to be to scale, so it doesn't really matter. That's isosceles as it comes. 100 millimeters. This side is 100 millimeters. Whose base length is 70. Perimeter, I don't have to calculate anything else to get the perimeter. I'm just going to add 70 plus 100 plus 100. 270 millimeters. That's my perimeter. But to do the area, 1/2 base times height. Do I have the height of that triangle? No. So got to remember a little bit about isosceles triangles and getting that altitude or the height of a triangle. So you're going to drop a 90-degree angle, or a perpendicular bisector is another name for it. That's what we call it in high school geometry, perpendicular bisector. So what that does is that blue line that I've drawn is the height. We need to find the length of that. Well, when you drop that perpendicular bisector, it cuts this down to 35. So it cuts the bottom in half. That's what it does to an isosceles triangle. Technically, if you have an equilateral triangle, equilateral triangles are also isosceles, but it does the same thing. Okay, so we're going to cut that to 35. So now we've got another Pythagorean theorem problem with a squared, b squared, and c squared. And Sam is excited about it. So 35 squared plus b squared equals 100 squared. 35 squared, 1225, 100 squared, 10,000. 1225. Subtract the 1225. $8,775. Take the square root. Second square root, 8,775. 93 point, let's see, label all given, round all non-exact area and perimeter values to the nearest tenth. Label all given measurements in your figure, and how to calculate necessary measurements that are not provided. Only use formulas that we've derived in class, so that's what we've done. So this is approximately 97.67. We'll go 2 decimal places. 97.67. 93, because I can't read. 93.67. Going 2 decimal places there, so I can round to 1 decimal place when I find the area. That's the reason for that. So that's millimeters. So the area, 1/2. The base length is 70, and the height is 93.67. So 0.5 times 70 times 93.67. Go 1 decimal place, so 3278.5. And it's square millimeters here. Yep. Okay. Do it now? Okay. All right. I'm going to go ahead and read number 3. A rhombus with diagonal lengths of 12 and 16. Hint, sketch your rhombus. Draw in your diagonals. Your diagonals cut your rhombus into 4 right triangles. They are exactly the same size and shape. Okay, so what's a rhombus? What's that even mean? It's kind of like a square parallelogram. I had a student that told me this in geometry class. She said, it's a square that got hit by a bus. It's pretty good. It's probably the best description I've heard in a long time of what a rhombus is. It's a square that got hit by a bus, so it knocks it a little crooked, right? So it's like a square parallelogram out of that. So a rhombus with diagonal lengths of 12 centimeters and 16 centimeters. You could draw this to scale, but we're not going to. I'm going to draw a rhombus which the sides are all the same length. But I'm just going to make it a little squished here. Trying to make them the same. That's pretty close to the same length out of that. And then you're going to have diagonals in there. So the diagonals, this is the long one. This is the 16. Didn't do a good job there. Do better. And then the other one is the 12. And it creates 90-degree angles in there. So from, A to B and C to D. So AB is 16. CD is 12. On the I'm just putting those letters on there so that I can talk about those sides and y'all know where I'm pointing at. Now, your diagonals cut your rhombus into 4 right triangles that are exactly the same size and shape. Also, the diagonals bisect one another. They're perpendicular bisectors to one another. So it cuts each one in half. So from here, from A to the center is half of 16, which is 8. And from C to the center is half of 12, which is 6. We're going to need that to find the perimeter, because now all we got to do is do Pythagorean Theorem to find how long our sides are. If we find one of them, we got the rest of them, right? Because they're all the same. So 6 squared plus 8 squared is equal to 6 squared this time. 36 plus 64. This works out real nice because that's 100. And square root of 100 is 10. So we know that the outside edge is 10 centimeters all the way around. Using Pythagorean Theorem. So that allows us to then use perimeter is 10 plus 10 plus 10 plus 10, which is 40 centimeters. It didn't even ask us to do that, did it? They just said draw it. Well, I got ambitious. Thought we were doing something cool out of that, but we weren't doing anything cool at all. We were just doing extra work. Oh, back up. The instructions at the beginning did tell us to, on numbers 1 through 4, do the perimeter in the area. So, I was right. Good job, teach.
I have a question.
Yeah. Maybe we can answer it.
The line that goes across is the baseline.
This is the diagonal that's 12 centimeters. That was the 6 is because the diagonals of a rhombus bisect one another. They cut each other in half. The A and the B are the ones that meet at the 90-degree angle. It doesn't matter which one's A and which one's B. C is always across from the 90, like away. Like, see how the 90 degrees are here? C is always across the triangle from it. It's always the slanted looking one. Maybe that's the best way to describe it. It's the slanted one. If you look at, but the A and the B always meet at the 90-degree angle. C's the other side. It is always the longest one as well. That's true. C is always the longest side too. Yeah, so maybe that helps too. All right. Now, area. So how do you find area of a rhombus? Does anybody know? Well, it's not a square, though. It's a rhombus. Squares are rhombus, but rhombuses are not always squares. Squares are always a rhombus, but rhombuses are not always squares. It's the product of the diagonals, actually. So 16 times 12, so area 12 times 16 Yeah, still on number 4 or number 3 there. To get the area, 12 times 16 is 192 square centimeters. The two diagonals, and that works for for a rhombus to do it that way. You could also, you think about the area of all the triangles added together can do it too. You can do 6 times base times height would be 8 times 6 is 48, and half of that's 24. 24 times 4. What's 24 times 4? 96. Oh, you got to do half. I forgot half. Half of 192. Well, if you're talking about area of a triangle, though, that's got the half in the formula, is how that works. We're finding the area of the rhombus, and there are different ways to find that. One way is to multiply the diagonals together and then take half, which half of 192 is the 96 that we're finding. And then if you take the area of each triangle, which there are 4 equal triangles, they're all the same size. The area of just this triangle up here in this corner is 1/2 of 6 times 8, which is 24. And 4 of those. No, because it's not square. Because it'd be 100, and it's not 100. It's 96. Almost 100, but not 100. It's kind of like an 88. It's almost an A, but it's not. So a rhombus is not a square, so you can't use the same formula unless you know the corners are 90 degrees, and we don't know that with this picture. That's and the diagonals would also be the same length if it were square. The measure from corner to corner is the same. If you're into carpentry and you want to decide if a room is square, you could measure from corner to corner, from this corner to that corner, and then go from that corner to that corner. If they're the same length, the room is 90 degrees at each corner. Instead of having to do Pythagorean Theorem, because not everybody carries a calculator around with them or wants to do it that way. So that if you're trying to decide if a room has 90-degree angles in the corners or is square, you can measure diagonals, and they should be the same length. If they're not, then it's not square. Number 4, equilateral triangle with the side length of 16 centimeters. What's equilateral? All sides are equal. So draw you a triangle. Try to make all the sides look equal. It doesn't have to be perfect. But when you label it, it becomes perfect. Here's yours. That looks almost equilateral. It's not perfect. It's pretty close. And so perimeter is really easy. 16 plus 16 plus 16. 48 centimeters. And this is just like an equilateral. We're going to have to drop a perpendicular to find the height for the area. You got to do that stuff. So 8 squared plus b squared equals c squared. 64 plus b squared equals 256. 16 squared. I'll make sure that I'm pretty sure that's right. Yeah, minus 64, 192, and then take the square roots. Whatever the square root of 192 is. 13.86. Go 2 decimal places. So the height is 13.86 centimeters. So we can find again the area is 1/2 times the base is 16. The height is 13.86. And we're going to round that to 1 decimal place because that's what the instructions told us to do. So 0.5 times 16 times 13.86, 110.9 square centimeters this time.
You didn't pull up this book, you didn't pull out your tractor because you know it's all of them the same, you drop it diagonal, drop it.
It's got to be a 90. It's going to be 90, yeah. Yeah, because it's equilateral. Remember, equilaterals and isosceles works the same way. You're just going to drop that perpendicular bisector between the two sides that are equal. Doesn't matter which side you pick on an equilateral because they're all the same. But if it's isosceles, you got to go between the two that are equal length. You got to drop down out of those. And I know it's going to be 90 degrees. I don't have to pull out the protractor to do that. Number 5 is kind of the same idea as the other ones that we did at the end of activity 13. It says calculate the area and the perimeter enclosed by this region. So to calculate the area, I would cut it into a triangle and a trapezoid and use it and then measure it with your ruler to get those lengths and width, length. Remember, area of a rectangle, or of a triangle is base times height. Area of a trapezoid, base 1 plus base 2 times the height. This is base 1. This is base 2. Where would you do another triangle? How? Show me how. Like here? You could. Yeah, you could do it that way and do a rectangle and 2 triangles. You could do it that way. There's lots of creative ways to do that one because you don't have any other measurements on there, and you're going to be measuring your lengths. So yeah, you could cut it into whatever. Yeah, you use your ruler and measure. Technically, to go off of what you're saying there, you could cut this into a bunch of right triangles or triangles in general if you wanted to. I wouldn't do it that way, but you could. Out of that, it's kind of like last week. We cut the shape, that polygon, into a bunch of triangles and then added up the 180s and got that formula out of it. It's the same idea here. It's just the area is going to be the sum of all the parts anyway. So use your ruler to measure there. You guys can do that. I don't think we need to coach you through that. DeAndre's got a garden, and it's shaped like an isosceles right triangle. And has an area of 648 square meters. DeAndre wants to put a fence around his garden. How much fence should he purchase? So we know it's an isosceles right triangle. So what does an isosceles right triangle look like? 2 of the sides are the same. And which 2 sides? Is it the legs or the hypotenuse? The legs have to be the same, so it doesn't really matter. I'm just going to eyeball it. I'm going to say they're the same. And there's my hypotenuse. That's not perfect, but it's close enough. I know it's a right triangle. I know the area is 648 square meters. I don't know the lengths of those sides, but I do know the formula is base times height. But what's special about DeAndre's triangle? It's isosceles, so the legs are the same, right? So really, it's 1/2 base times base, right? Because they're both the same. Or you could say height times height. It doesn't matter which one you call it. They're both the same length, right? So area is 1/2 b squared. Don't we know how much the area is, though? 648. We are gonna do a little bit of algebra here, and you should be happy because everybody loves algebra, right? How do we do that? multiply by 2 or divide by half, whichever way you want to do it, doesn't matter. I'm going to multiply by 2. And that'd be 1296 equals b squared. And then I'm going to take the square roots. The square root of 1296, 36. So each side of DeAndre's, or each leg of DeAndre's triangle is 36. But we don't know how much the hypotenuse is. Because we got to find we got to buy a bunch of fence in here. We need to know how much to buy. So far, we're not enclosing the entire garden. So some deer are going to get in there, or some carrots are going to run out, or something weird's going to happen. So we got to find that length. So 36 squared plus 36 squared equals c squared. So 36 squared plus 36 squared. 200 or 2,592. 592. And then I'm going to take the square root of that. 50.9. Oh, it says round to the nearest hundredth of a meter. Sorry, I didn't read the last line of the problem. So I'm going to go 9.1. Doesn't really make it that much difference, but. And then we got to find the perimeter. 36 plus 36 plus 50.91 centimeters. Or that's what it'll end up with it. So 72 plus 50.91. Pretty boring thing here. 122.91. Not centimeters, it's meters. Why did I put centimeters? That's a tiny triangle if it's centimeters. For a garden anyway. So we need at least 122.91 meters of fence. I bet we got to buy 123 when we go to the store. They don't sell us in 0.91s of that. So easy enough. All right. So the last thing is kind of a challenge thing for you. So you got you can find this on YouTube or whatever if you want to. It's a little animation of how to do this, but the idea is that you take that last page and you can cut those out, and then try to follow the instructions there. Use the figure in the next page. Cut out the squares built in on side AB and side BC, the shaded ones, and show how you can cut these two squares in a way to make them fit inside of this larger square. So it's a geometric proof of the Pythagorean theorem. Okay. So if you can do that and bring me that back drawn in here, I'll give you some extra credit on the test next week. I think everybody should be able to do that. I'm okay with you using Google to help you. That's fine. Whatever way you need to. Just don't make confetti out of them, because then that'd be too easy to just jumble them in there. They should be in somewhat geometric shapes.
So we just have to make, these two squares have to get into this square.
Yes, ma'am, that is correct. All the pieces, yeah, and it fills up that square.
Glue it in there and put it down.
Yep.
So we're gonna have a test over 16.
And last week's.
So we have to do homework.
Yeah, I got them. You might know how long Subway was online order. Not there to pick it up on time.
Do you want us to go ahead and put this back out?
It's up to you.
Can I get a chance for the test?
Yeah.
Can I give you?
Yes.
These are easier.
Yeah, those are already easier than these. Yeah. Okay, all right, just want to make sure. Zach, your homework's on the desk up here, or up here is fine. And we'll go from there. Next week, I'll let you know by Friday for sure about the test. It seemed to bode well for you guys on the take-home weekend. So, I'll I'll let you know by Friday for sure. Probably before then. Just give me a chance to breathe.